First up, we need to complete the square. So factorize the 2 out, just at the first two terms. And then with x squared plus 3x, it's going to become x plus 3 over 2 squared minus 3 over 2 all squared, which is 9 over 4, plus 7. Just because I fancy it, I'm going to talk very quickly about why this method works. I think it's always interesting to come back to it because we have a rectangle here and it's got sides x and then x plus 3 actually, because that's what x squared plus 3x is. So we can split it into a square and a rectangle, x squared and 3x. So what we then do is we basically split this bit into half. And in fact, let me do it on a separate little diagram. Okay, so that is the square that I've cut in half. And I'm just going to have this little bit here. It's going to now become 3 over 2. What happens to the other bit? We move it over here. So I've now got a square, which is x plus 3 over 2, all squared in area, this term here. But I've got this missing bit, and that is the 3 over 2 times 3 over 2. That's the bit that I have to subtract. So this method was known like thousands of years ago, and that's basically how it was first invented without sort of doing it algebraically by doing it geometrically. Okay, back to this question. We're nearly there. So it's going to be 2x plus 3 over 2 all squared minus 9 over 2. And then I'm going to write the 7 as 14 over 2 because then I can, without a calculator, put them over a common denominator. So it's going to be plus 5 over 2. Okay, there we go. For B, we're asked to state the minimum. So, I'll very quickly write down the answer. It's going to be minus 3 over 2, 5 over 2. The reason being is that this term that I've just underlined is always going to be greater or equal to 0. It's a square number. It's going to be positive. There's no way it can be negative. So it's always greater or equal to 0. So the smallest that it could possibly be would be 0. And therefore the smallest the whole function could be would be 5 over 2. And the value of x that gives this equal to 0 is minus 3 over 2. So that's why you always take the negative here of whatever this part is, and then you just take this as normal. So there we go. There's our minimum. Finally, we're hence to deduce the minimum value of this thing. Okay, we've got tan involved. This is a slightly different. But as you can see, there's a striking resemblance with our original function. So we're going to go for exactly the same. We can just basically replace x by tan theta. Okay, and again, the minimum's actually going to be 5 over 2 because this thing is still, it still can never be negative. Thing is, it doesn't actually ask, oh no, it does ask us for the minimum, so I've dealt with that bit. And then we want the smallest positive value of theta for which the minimum value occurs. So again, it's going to, well, last time it was when x is minus 3 over 2, this time it's going to be when tan theta is equal to minus 3 over 2. So we've got this equation to solve. Okay, we're working in degrees. So we're going to get a negative answer out, minus 56.3. going to write it down. But actually, it's the next one. I need to add 180. So 123.69. And it says smallest value in degrees. Okay, I'll probably write 124 degrees. And the minimum here. Just for just to show with the graph where that came from. So I can draw the graph of tan x, and I managed to find this point here, but I wanted a positive value, and tan x doesn't have the same symmetry that sine and cos have when you're finding other values, but in fact all you need to do to get to the next one is remember it's periodic. The 180 degrees repeats every 180 degrees, so just added 180 onto it to get this point here, which was the value of theta that then gave tan theta is -3/2. I quite like that. It's like slightly different take on completing the square. So yeah, good part C in particular.